In this video, we'll look at how to create user-defined functions in R. Now, we've already seen, in fact, that every command in R is itself a function because it requires certain inputs, certain arguments, and it will then return a value which can be stored in a variable. But in R, just as in all other programming languages, you can create your own functions. And these can be very useful, and as we'll see, it helps you again to make more use of R and to speed up your use of R and your R code. So what I'll do first of all is to show how to create a simple function showing the syntax, and then I'll look at a concrete example showing how being able to write a user-defined function can assist you in your R work. So let me first of all show how to create a function. So here's the syntax. So what you do is you have to assign a function. A function is an object, just like any other object in R, so it has to be assigned to a variable. So I'm calling, which is in fact the name of the function in effect. So I'm calling this function f, that's the variable into which I'm assigning, there's the assigning operator, this function. So it's f, assignment operator, then the word function, and then in brackets you specify the arguments to the function, the inputs, the data which the function will use. Now you can, as you can see here, you can have two or more arguments, and the arguments are given variable names. In this case I'm simply using x, and notice they're separated by commas, so I'm simply calling the variables, the arguments here, x, y and z. Notice that x and y are simply, the letters are simply there, whereas z has got a what we call a default value attached to it. You can, in R, assign default values to arguments, and they will be used within the function unless you override them in the function call, as we'll see. So I'm not specifying default values for x and y, but I am for z. So unless I override this value of z in the function call, it will use 10. So having specified the arguments in brackets, you then use braces, as we've seen before, to encase the block of code, which is the code that the function will run, using the values that are inputted into these variables. So as you can see, this function is very simple. All it does is simply add together those three values of x, y and z, which is then assigned to a variable total. Then in order to return that value so that you can use it, you use the word return, and in brackets what variable what you want to return. So I'm going to return the value of total. That will be returned by the function, which could then be stored in a variable itself. So it's very straightforward. Function name, here the word function, in brackets the arguments, the code which uses these arguments, and then the return statement to return some value. So I'm going to enter that function now. You just need to put you can either highlight the whole function or simply put the cursor on the first line, press Command Enter, Control Enter on Windows. That has created that function, and as you'll see if you go down to the environment, there we have it. A function is an object just like all other objects in R, matrices, vectors and so on. So it appears in the environment. You can view it by clicking on this little icon here, and there's the function. Now to use the function, you call it by name, and you in brackets you give values for these arguments. These are called the parameters. So as you can see here, what I'm doing is I'm calling this function f by using the name of the function f, and then in brackets I'm specifying values that will be inputted into these variables, which will then be used within the function. Now the order, of course, in which you put the values here will match the order here. So clearly I'm specifying a 4 here for x. So x will take on the value 4. Y will take on the value 2. as I'm not specifying a value for z, it will use 10. So when I run this function, when I call the function here, this should return 4 plus 2 plus 10, which of course is 16. So let's run that. And that's exactly what we get. It's returned a single element vector containing the value 16. Now I could of course have assigned that to a variable itself. So I could have put, say, m as a variable, which then the assignment operator, and then this, and the value of 16 would have gone into m. Here I'm going to call the function again, but this time notice I'm overriding the value of z, the default value of 10, and making it 12. So this should return 12 plus 7 plus 3, which is 22. Get that. Again, I'm going to call the function again. Notice here that I'm actually using the name of the argument. You can do that. You don't have to, as you've seen here. But it's possible to specify the argument name. So here I'm specifying 12 for x, 34 for y, and again I'm overriding the default value of z using 45. Notice I'm actually saying z equals. I'm using the argument name here. So this of course will return 45 plus 34 plus 12, which is 91. And final way you can call the function is to specify the argument names for all the variables, or for just 2 of them. And so here I'm calling it again, setting x equal to 3, y equals to 9, z equal to 20, so that's going to of course return 32. So as you can see, in actually calling the function, it's quite flexible. You can either you can specify the argument names if you wish, or not, and you can mix that. You can specify some and not others. So that's entirely up to you when you call the function. Now, one very important point to note about functions is that the variables within the function, the arguments here, and any variables within the function, so in this case x, y, z, and total, these are what we call local variables. If you've done any programming before, you'll know what I mean by that. These are local rather than global variables. And what that means is that the values of these variables only exist within the function, and only exist when the function is actually running. Once the function has stopped running, those variables disappear. Now I can prove that by trying to print them out. So if I try to print out the value of y here on the console by simply typing the letter y and entering it, as you can see, object not found. That's also demonstrated down here in the fact that those variables, those objects x, y, z, and total are not here in the environment because they're not actual global variables. Once the function is run, once the function call is run, those variables no longer exist. So again, z is not found, x is not found, total is not found. They're local variables. They only exist within the function. What this means is that you could use the same variable names outside of the function and there wouldn't be any conflict. So I could use x, I could use z, and so on in other functions or outside the function, and there'd be no conflict. It wouldn't, R wouldn't confuse the two. Sometimes it's very useful to know that. Okay, so that's how we create a function and call it. Let me now look at a much more concrete example of where being able to create your own function could be very useful. Now remember when I did the video on time series analysis, or rather regression with time series data in R, then of course one of the standard diagnostic tests is with time series data is to test for autocorrelation of the error term. And you can do that of course with the Durbin-Watson test or the Broish-Godfrey test. Now if we look back at the code that I used for the time series video, the regression with time series data, here it is. So I created, I imported some time series data, I modified it, I changed it into log and so on. We went through that. I then ran an equation here showing how to use the lags and differences. Remember, you need the DIN package in order to do that. And then I then ran some standard test of autocorrelation, the Broish-Godfrey test with first order testing for first order correlation and then second order. And later on down here I ran the DW test. Now I did those all separately. Notice here that if I wanted to test for first order, second order and maybe others, I would have to run them all separately. By creating a function I can automate that and run it much more efficiently. So what I've done here is I've created a function called AutoTST, essentially stands for autocorrelation test, which has three arguments. Mod, which is the LM object, which is required by the BG test function and the DW test function. So notice that the value that goes into mod when you call the function will then go in here and here, which is needed in the functions. Orders, because the BG test function, BG test command needs you to specify the order of autocorrelation, and type, because that also needs to specify the type. The DW test function simply needs the LM object. So in order to run these autocorrelation tests here using BG test and DW test, I need to the function needs to access the required information. Notice for mod I haven't set a default value because that of course will be the whatever LM function, LM object you pass to the function. But for orders I'm setting the default value of 1. Remember with the orders you need to specify a vector of values, some value rather. Here I'm going to specify a vector so that I can then loop through it. But initially I'm just using a value of 1, so it will do first order correlation unless I override this default value. And for the type I'm specifying a default value of chi-squared, so it does a large sample chi-squared test. Again, I could overwrite that by using f to do an f test. So the function requires these inputs, these arguments, which will then be used within the body of the function here. Now, to run the BG test, I'm going to loop through the vector that's in orders. We saw in the previous video how to loop through through a vector using the for statement. So as you can see, I'm going to loop through orders, assigning the value, each successive value to t, which will then be used in the BG test function here. So if I specified orders here, say 1 and 2, it would first have used 1, so first order, and then 2. So again, I think you should be able to see how I'm using the for loop here to run this test a number of times for different orders of integration. For the DW test, of course, you simply specify the LM object here, so that's quite straightforward. Now, just one other thing here. Notice this line here, which is a very important line, which you find in many functions. This is how you test to see if the package that you need to run these particular functions. Now, of course, remember BG test and W test are in the LM test package, so you have to make sure that's in memory. All these, of course, you get an error. And the way you test to see if it's in memory, and if not, load it up, is using this standard line here. So you use a simple if statement. You put if, and then in brackets you put the word require with an exclamation mark. The exclamation mark is the not operator. So and then the package that you're testing to see if it's in memory. So basically what this says, if require isn't, if LM test is not in memory, require it, put it into memory. And that's the standard syntax. If you look at some of the actual functions in some of the packages that you've installed, you'll see many of them have this particular line. Now the big advantage of this line here, using an if statement, is that rather than just putting require lmtest, is that this will only load up lmtest if it's not already in memory. You'll see that when I run this function later on, the first time I run it, because lmtest is not in memory, it will load it up. The second time it won't, because it's already there. So this is the standard way you test to see the package that you need is in memory or not. And if not, it will load it up. Okay, so that's the function. So let me run this command to create the function. So if I look in the environment, you'll see the function is now there, the object. And now let's look at how we can use this to automate testing for autocorrelation. So what I'm going to do is I need of course some LM object. I need to run some regression on time series data. So I'm going to repeat the regression, the first regression I did here using this in the video on regression with time series data. Now, of course, because it's code, and I can run this in one go very quickly. Of course, is the benefit of writing code rather than using a manual-driven package. So I'm going to highlight this first few lines, so it will input the data, create it, and modify it, turn it into logs and so on, do everything that's required, and then we'll run this first regression here and summarize the result, show a summary of the results. So let me run that, and there we are. That's the results of this first equation. So I now have an LM object. I've now run a regression, so I can test for autocorrelation of the error term here. So notice that so if I go back to here, notice that I now have fmod1 as my LM function. Okay, so I'm now going to call this autoTST function, specifying the various arguments. So first of all, it needs to specify the LM object, which is fmod1. I'm then going to specify a vector for the orders argument here. In other words, I'm going to test for first order, second order, and fourth order autocorrelation. So this for loop here will loop through those values 1, 2, and 4 in turn, putting it into the BG test function. So it'll first of all test first order, second order, then fourth order. I haven't specified any value for type, so it'll use the default value of chi-squared, so it's going to run a chi-squared test. And then of course it will do the DW test on fmod1. So if I run that, as you can see, we get exactly what we wanted here. It's because I used a function, I've made it much quicker and easier to run tests for different orders of autocorrelation and the Derby-Watson test, rather than putting all the lines in separately. And notice too that because having not run this function before, lmtest was not in memory, so it did load it first time off. So as you can see, by writing a simple function here, I'm able to automate testing for autocorrelation, make it much more quicker and flexible. And of course, you could add additional commands into the body of the function. If you wanted to, you could, for example, modify this and make it both a test of autocorrelation and, say, heteroscedasticity into more general testing procedure, in which case you'd simply need to add the required commands into the function. Now, if I want to run it again, this time using an f test, in this case I need to override the default value of type, so I'm putting type equals f. I'm still testing for first order, second and fourth order, and of course I'm testing the results, the equation fmod1. So let me run that. And again, very quickly, notice this time no line here saying liquid by package lmtest because it's already in memory. So this if statement found that LMTest was already in memory, so it didn't need to require it, didn't need to load it again. Okay, so that shows you, that's a good little practical example of how being able to write user-defined functions can be very useful. And if you can get to do this, you'll find that you can make even more use of R and RStudio. Now, of course, the other benefit, of course, of writing code and writing functions is that you can save them. You don't have to write this separately every time, of course. Once you've done some nice programming and created functions which you'll want to use again and again, then simply save them, and then you can load them back in and run them. So how do we do this? Well, very simply, to save a function into your working directory. Now, if you look at the files panel here, then you'll see it shows a particular directory. Now, when you use the save function, it will save it into what is your current working directory. Now, this may or may not be the one that's currently showing here. If you're not sure, you can go to the More option here, and you can either go to the working directory, or you can set this directory that's currently showing, this folder, to be the working directory. So I'm going to do that here, just because I want to put the function into this particular folder, this particular directory. I think that this is my current working directory, but I'm not sure. You could run a simple command to check that, but I'm simply going to set this as my working directory, which, notice, uses the setw command, so you could have typed that in here yourself if you wished. So I now know that when I save auto this function, it will go into this directory. So let me save it. Now, to save it, use the command save, in brackets the name of the function, comma, file equals, and then some file name. In inverted commas, of course. So let's run that, and that has saved it. Now if I simply refresh the directory here, the file listing, there it is. It's been saved in my working directory, which is currently this one. Which means that I can then, later on, when I'm running, doing analysis and running, and I need to do auto-correlation tests, I can simply load this back in to memory and use it. You can see that if I, let me just go back here. Let's clear the console. Okay, so as you can, this of course is still, I saved it, it's still here in memory. So what I'm going to do is to remove it from my environment, remove it from memory, which of course you use this little icon here. Click the one you want to remove. Otherwise, if you click this, it will ask you to remove all of them. I just want to remove the function. One object. Okay, it's no longer there. Now, of course, this means if I try to run it again, you'll see it won't work. So let me try that. Cannot find it. So what I need to do is to load it back up. Now, the command for that is, surprisingly, load. Simply put load, and then in commas and inverted commas, the name of the file containing the function, which of course was auto test. Again, if you don't specify an actual path, it will load it from your current working directory, so you need to make sure that the directory in which contains auto test is your current working directory, which of course it is in this case because I already told it to do that. So let's load it up. If it can't find it, of course you'll get an error. Now if we go back to the environment, you'll see of course that it's back, which means I can run it again. I can now run it, so let me run this command again. I call the function, and there we get the 3 autocorrelation tests, 4 rather, including Derby and Watson. Again, because LMTest's already in memory, it doesn't load it up. So that's how you can save and then load functions back up. What if you want to edit a particular function? Want to add more code into it, for example, or more arguments? The command to do that is fix. So what you put is fix, and then in brackets the name of the function. Obviously the function has to be loaded up, has to be in your environment, otherwise it's not going to find it. So if I run this command here, fix auto tst, what it brings up, as you can see, is a separate little window where you can modify the function, you can edit it and so on, and then save the modification. So what I'm going to do here is to add a comment line to tell me what this function does. It's a good idea when you're creating your user-defined functions to have comments in to remind you what the function actually does. Because if you don't have sometime in the future when you come back to it, you may not be sure. So we need the hash, of course, for the comment. So I'm going to say that this performs auto correlation tests. I'm going to save that. That simply saves it into memory. It doesn't save it on file. As you can see, if I look back here, this we now the time is still as when I originally saved it. So I'm going to save it again here, which puts it back in. And as you can see, it's now saved it again. The time has changed to the current time. So let me now remove it from memory, load it back up, and we'll see we've got the new, the edited version. So I'll remove it again from memory, like that. Obviously, if I try to run it, we now get an error. So let me load it back up. Okay, so it will now run. And if I finally have a look at it, here it is. You see we're getting the edited one now. It's got the edits in. So that shows you how you can easily edit and modify functions once you've created them. So you can easily save them and load them back up. So I think that shows you how very useful it is to be able to create your own user-defined functions. And it's something that if you want to make the most of your knowledge of R, you should have a good look at.